Okay, this is part two of lesson 2B, unit 2B. These are the homework from yesterday, answers and questions. Okay, interpreting correlation. So we're going to learn about correlation. This is a big thing with stats. Correlation R gives the direction and strength of the linear association between two quantitative variables. I made sure to emphasize linear because that's the part students forget. Usually they go, okay, yeah, strength and direction, but it's only to be used with linear association. So if it's a curve graph, correlation's almost irrelevant. It's just not what we're looking for there. Correlation only goes between 1 and -1. I think it can be 1 and -1, so it includes those values. It's inclusive there. If it's a positive association, we talked about that positive slope, then the R is going to be positive, the correlation is going to be positive. If it's a negative slope, negative association, you're going to have a negative R. But -1 and 1 are perfectly strong. Actually, 0 is when it gets weak, when it gets closer to 0. So extreme values occur only in a perfect linear relationship, and the points lie exactly on the straight line, on the regression line. That would be very rare to have perfect data like that. If the relationship is strong, it would be closer to 1 or -1. If it's weak, it's going to be close to 0. So it always ranges between 1 and -1. Closer it is to 0, the weaker it is. The closer it is to 1 or -1, it's very strong. And so it describes strength and direction for a linear association. So let's just approximate. That first graph there on the left top, I don't know. It looks pretty weak, at almost no association or very little. So I'm expecting something close to 0. It says it's R equals 0. It's going to be not very big. Next one, the looks like a negative association. It's trending downwards there, so but kind of weak. Maybe negative. Wait, negative 0.3. Yeah. Okay. Next one is positive, maybe a little bit stronger. I don't know if that's positive 0.4 or something, 0.5. That's fine. Sorry, the next one is negative, a little bit stronger, negative 0.6 or negative 0.7. It's closer, getting closer to one. It's getting stronger as we go here. So the next one, a little bit stronger, definitely positive. So maybe 0.8 or 0.9 there, I'm guessing. And the last one, that's pretty strong. So I don't know, 0.97 or something, 0.99. It's negative. Oh, sorry. So I was so focused on how strong it was, I forgot to say it's a negative association. So the R, the correlation, would also be negative. Okay, here's a scatter plot we did before about the WNBA players, where R equals negative 0.427. So you can see that, I guess we call it moderate or moderately weak there. So the negative association, interpret the value of R. So the linear, you want to say something like the linear association between height and free throw percentage is negative and weak or moderately weak, is what they said. Correlation of R equals negative 0.427 indicates that the linear association, make sure to use that word linear there, between height and free throw percentage is negative and fairly weak. It's pretty good. Include context by using the variable names. Height and free throw percentage need to be part of your interpretation there. It's the context. Correlation doesn't imply causation. We get it more into this in future chapters, but we're going to mention it now. So here's some interesting data. So revenue from skiing, okay. The number of deaths from tangling. And what tangling, I think they're talking about becoming tangled in your bed sheets. I don't understand. I guess that's a way that you can die. I didn't realize this was a thing. So there seems to be a pretty strong positive correlation. So as you make more money from skiing in millions, there are more deaths from tangling in your bed sheets. Okay, that's strange. So should we not ski anymore? Should we just close down all the ski resorts? Because evidently there's a strong correlation. Maybe that's causing people to get tangled in the bed sheets. That doesn't make sense, right? So even though it's a strong positive correlation, 0.97, but maybe there's some other reason that's causing. I don't know what the reason is, but there might be some other lurking reason there. And we're going to learn more about that in Unit 3, but just keep in mind if a question implies that correlation, strong R value, is, it's causing the X variable is causing the Y variable to happen there, that's not true. So that's just, silliness. So sometimes it's going to be more tempting than that one, but don't fall for it. So correlation does not prove that. It's a big stat concept. Scatter plot shows the speed in hours, or the distance, in fact, in feet needed for a motorcycle to come to a complete stop. Okay, association is curved. The correlation is R equals 0.98. Ooh, that's weird. How could the correlation be 0.98? Because again, correlation is measuring linear strength, but you could use correlation with a curved graph, but it doesn't tell us anything. It's not, it doesn't mean the association is linear, right? So correlation is measuring the linear strength. So, but when it's not linear, you don't want to use it. It's not really valuable there. So yes, the data could be, pretty good curved data, but it's not something we want to use because otherwise you're going to think correlation. You're going to think, oh, it's 1 or -1. It's perfectly linear, but it's not necessarily linear. But we should only use correlation to describe linear, because again, it's an indication of strength and direction of linear strength there. The linear relationship between two variables. The scatter plot shows the relationship between chocolate consumption and number of Nobel Prizes per 10 million residents for a sample of countries. Where's the United States? Kind of in the middle there. So, wow. I think we need to eat more chocolate. We would have many more Nobel Prizes, I think. Switzerland evidently is pretty dominant in Nobel Prizes. And they eat a lot of chocolate over there. So maybe we should do that. But actually remember, just because this may have a strong correlation doesn't mean that eating chocolate is causing more people to get Nobel Prizes. There might be another variable around, a confounding variable that we will learn about later. Not all questions about cause and effect use the word cause. So make sure to read headlines in the newspaper or things. Sometimes they imply causation, but they don't actually use the word cause. How to calculate causation. Okay, so how to calculate correlation. So I'm going to show you these steps here, but we're actually going to do it. I think that will help you here. Very similar to the idea of standard deviation. Typically, you don't have to solve this by hand, like do all these steps. Typically, the calculator is just going to have a question and, it'll do the correlation for you. If you type it in your calculator, do regression, which you'll learn how to do. But it's nice to know the concepts behind it and understand it. Occasionally, there is a question where they give you all this data, not the actual data, but these values like standard deviation and so forth. And sometimes you might have to do this. It's possible. So I want you to understand that. So just kind of follow along. I don't even care. I want you to type the data into your calculator. So let's just kind of, so here it is. Okay, so type that data into your calculator. It'd be good to do right now. So type all of that in there. I already typed it in, so that's that. So you can stop it and type it in if you want. Okay, so I'm going to use this formula. So let's go step by step in this formula. So what this formula is saying, if you look at the right here, it says you're going to take x1, which are all the hand spans there. Those are all the different, like 19, 21, 18. Subtract the mean of all those hand spans, mean of the span, divided by the standard deviation of the span. Take those numbers, multiply all those by the same version of that for y, sum all of those up, that's what that sigma means, and then multiply that by 1 over n minus 1, or divide that total by. And we're going to do that step by step here. So first we're going to call this sum x. What do I call that? I'm just going to call it xx. Okay, for just we're doing that first parentheses. Okay, so in the equation bar, I'm going to hit equals. Control divide. If you look at the bottom of the screen, it's easier to see. So at the bottom of the screen there, you have a fraction. So I'm going to put it in span there. That's my x1, each one of those values, 19, 21, 18, minus the mean of span. Just follow along. So I'm subtracting the mean of that whole list. And then I'm going to get standard deviation. I don't remember the command. I'm going to go to here. It's called standard deviation of the sample and of span. So I'm getting the standard deviation of span. So I'm going to press enter, and it should generate all those different values. I'm going to go here, call this YY. Same thing, but for the Y variable here. So control divide, if you look at the bottom of the screen. So this one's called candies, minus the mean of candies over, I'm going to go back to the catalog here, standard deviation of the sample of candies, and get all those values. And they look weird there, okay. So now we're going to, I'm going to call it multiply, so M-U-L-T, or I'll just call it multiply. So multiplying those values, so I'm going to multiply XX times YY there. So, oh, beautiful. We got all those numbers. Those look great. Now we have to, so multiply is each one of those totals. So we have to sum those up. So I'm going to go to a calculator page. Say sum of multiply, that whole column. Is that, I'm going to divide that by n minus 1. N is 24. There were 24 different pieces of data there. So 23 would be n minus 1. And I get 0.8348. So let's just kind of remember that number. So I'm going to do it the calculator way now. So the calculator way is to, if you have the data in your calculator, go to menu, stats, start calculations. We've done this before, menu 6.1, but instead of 6.1.1, we're going to go to 3 or 4. I prefer 4. Statisticians tend to prefer 4. A plus BX is the form we usually use for stats class. So click that for linear regression, choose the list. I think the first list was span. The Y list was candies. And you can just press enter here, and it gives you all this information, right? It gives you the equation of the regression line. It actually put it into F2 for me automatically. Gives you R squared and R. So it gives you R there, which is 0.830. Does that look familiar? If you remember that number, that looks to be the same number we got there for R. By the way, just a side note, if you hit variable and go to stat R, that stores that number in there. So it's there. You could access it if you need it. Once you do regression, it stores a bunch of variables in your calculator for you. So that is the correlation. R is the correlation, not R squared, but R is the correlation there. Okay, they go through the same steps I did, but I think mine was easier to understand. They got the same answer. They rounded theirs. Theirs is a little bit off because they rounded all those numbers each time they did it, and we rounded at the end. This is great to know for multiple choice questions. You really want to know these guys right here. So correlation requires that both variables be quantitative. So it makes sense to do the arithmetic to indicated by the formula for R. So it's quantitative variables. Both variables have to be quantitative. This is actually interesting. Correlation makes no distinction between the X and the Y, the explanatory and the response. You could switch them. Correlation remains the same. So it doesn't matter. That's actually a test question. You're going to see that. So R uses standardized values of the observations. R does not change when we change the units of measurement of X, Y, or both. So if we changed from measurement from inches to centimeters and replotted the data and reanalyzed it and redid linear regression, you get the same R value. So, standardizing scores, put them z-scores, whatever you got, it's not going to affect R. Correlation R has no unit of measurement. It's not standard deviations, it's just R. It's just a number between 1 and -1. 1 and -1 are stronger as it closer to those numbers, and 0 is weaker, right? So here's a quicker method. That means use the calculator to do regression, and you got it. Okay, let's just do a couple practice problems. You're done with the lesson. These are just practice. Scatterplot shows a relationship between the maximum drop in feet and the top speed of 10 roller coasters with the largest maximum drops in the world. Because of ties, 14 roller coasters qualify, but only 13 are shown since 2 roller coasters have identical values, 255 and 85. I guess it's exactly the same. That's interesting. So they're at the same point. That's like a double whammy there. For these data, R equals 0.947. Interpret the value of R. So R equals positive 0.947 is the linear relationship between maximum drop and top speed of a roller coaster. And it's positive and strong, something like that. Let's see. Linear association between maximum drop speed and is positive and very strong. Good. You may know that Texas is the largest oil producing state in the US. You may not know that North Dakota is also a large oil producer. Correlation between the year from 2001 to 2020 and the oil produced in millions of barrels is 0.943. Does this mean there's a strong positive linear relationship between year and oil produced? Explain your reasoning. So does an R value mean for sure that it's positive, strong, and linear? We saw one example in the notes. Doesn't mean it's linear. Sometimes they misuse R. Sometimes people use R it happens a lot. Mathematicians do it all the time. Statisticians don't like to misuse R. So it doesn't mean it's linear. That's what we don't know. So maybe the data looks like this, right? So maybe the data is exponential or some other curve, and so it doesn't mean the relationship is linear. We can't really say that just by knowing the R value. We'd have to see a graph or something else. This one I don't think we're going to do, but you would type it in your calculator if you want to try this one. Good practice. See if you can do linear regression, get the R value, and I would not do that by hand. I would do linear regression to get the negative 0.805. Again, it just tells you the R value when you do linear regression, which is super nice. Okay, that's your lesson for today.